Okay, so we will continue with our um, second unit, and this second unit completely what we will do today is the portions for the second test also. So we will cover all of this unit through these online materials that I'm going to send over the next few days. So one of the most important properties of digital circuits is timing, and the first part of this unit is completely related to timing. How can we change the timing? How can we reduce rather than change? How can we reduce the timing of any circuit? So before all that, we will just look at some basic definitions. The first definition is propagation delay. So this is a delay between input and output. We have an input waveform, we have an output waveform. What is the delay between the two? That is 50% of output to 50% of input. That is called as the propagation delay. And another one, we will come back to this contamination delay. Another important metric is the rise time. This is for one single waveform. That is generally the output waveform, because input waveform is not on our control. Output waveform is rising or falling. How much does it take from 20% to 80%? That is, if it is falling, how much does it take from zero point 0.2 VDD to 0.8 VDD? That is called as the fall time. Similarly, rise time. Okay. Now, one more delay that we will mention here, and we will use this more in the last unit when we are talking about slew and all those other timing measurements, is contamination delay. Contamination delay we might not have heard before. This is how much time does it take for any change to be seen in the output signal. Okay, that is, we are changing the input. Okay, and for some time the output might not change because there are a few logic gates, and the output will be at the same value, and after some particular time the output will start changing, right? And then how much time does it take to reach 50% of some value? That is, we might start at output 0, and it might oscillate a few times because the input is changing and there are multiple paths from the input to the output. One of them might be fast, so that is causing the output to change, but the other is slower, that is also causing the output to change a little bit later. But among all these, the first one, okay, that is a measure of contamination delay. That is, output is getting contaminated. Output is at some value, right? 0 or 1, but after a very small amount of time it begins to get contaminated, and that particular timing is called as contamination delay. Before it, it is pure. That is, it is at a perfect value. After this, it is not at a perfect value anymore. So this is a new timing definition, which is also called as contamination delay. Before we continue, just one question that you can think on. We have defined propagation delay, contamination delay. Of these two timing definitions, which do you think is going to be larger for a circuit in general? It will have some propagation delay, it will have some contamination delay. Which do you think is going to be higher? This is something that you can think on. Later on, we will discuss the answer also. Okay. So this is a pictorial representation of the things that we discussed. TPD. Okay. PD is generally propagation delay, and we have added this F to show falling. And again, this is also propagation delay, but rising. And most important to note, this is between two waveforms. This line is corresponding to input waveform. This line is corresponding to output waveform. So between these two waveforms, what is the time? That is called as the propagation delay for rising, because the output is rising. This is output falling. So this measures the propagation delay falling, and average propagation delay also we can define as the average of these two numbers. And similarly, we also mentioned fall time and rise time. This is for one waveform. This is not for two waveforms. Any single waveform, generally output waveform, how much time does it take to go from 0.8% of its initial value to 0.2, not 0.8%, 0.8 of its value to 0.80% to 20%. Similarly, 20% to 80%. So another important concepts related to timing is the charging and discharging of a node. Okay, in VLSI, digital VLSI especially, we have only two values. We have 0 and VDD. We don't have any other values for the output signals, and generally we are concerned about how much time does it take to go from VDD to ground and ground to VDD, and generally we call that as charging and discharging. And two more things: the driver, that is, we have a gate. The gate output is being controlled by the logic, and that gate is called as the driver gate because it is responsible for the output signal. Generally nowhere in the circuit you will see two signals that have the same driver because there will be some conflict. I have one output that is maybe going to 0, and I have another gate that is driving the same signal to 1. That will be a problem. It will be at an intermediate value, and that is a huge problem. So generally every signal will have one driver circuit, exactly one, and not 0 also, because every signal has to have a proper value, 0 or 1. And the load part of a driver is the total capacitance that is connected at the output node, and this is not just itself. So if you look at any wire, for example, like we discussed just now, it will have a driver, that is maybe some NAND gate or a NOR gate. It is driving the value of that particular signal. That is the driver part. But also it is connected to some other gate. For example, a NAND gate might be driving the input to another OR gate or an AND gate. So that gate is called as load part. So together, the driver and the load, all these will be connected to the same signal. The driver will be driving the signal, and the load is the one which is getting the output of the driver.